Okay, this is lesson 3.5. We're going to be talking about rational functions today. This is from Mrs. Cucci's College Now Pre-Calculus class, so please make sure you have lesson 3.5 open and ready to go. All right, so by the end of this lesson, you will be able to, for a rational function, find the domain and graph the function, identifying all of the asymptotes. You'll also be able to solve applied problems involving rational functions. Now, this lesson may span a few days, so just be aware of that before we begin. Okay, so a rational function f that is a quotient of two polynomials. Okay, so that means if I take one polynomial divided by another polynomial, p of x and q of x, what I get, f of x, would be a polynomial. My domain is going to be all of the values except for the value in the denominator for q of x that would make the function undefined. Okay, so again, you guys have done a lot of these, figuring out what domain is and how to determine what value would make a function undefined. So let's look at the first one. The domain of a rational function, we're going to talk about f of x equals 1 over x minus 3. Okay, so with this function, there's a few ways we could look at it. We could look at the graph of it and determine from there what our domain would be. Okay, so what I'm going to do is I'm going to insert a graph page, Control I, add a graph, and I'm going to graph that function, 1 over x minus 3. Okay, and this is what I wind up getting. Now, if we look closely, we notice that we seem to have something going on in this area here, okay? All right, something seems to be happening here. Doesn't look like we're going to have anything that exists there. And another way I could figure that out is I can go and look at the table there and see what's happening at that value. And if we see we've got when x equals 3, the function becomes undefined. And we know that if I look at the actual function itself, if I were to plug in 3 into the denominator, that value of x, 3 minus 3 is 0, which will give us 1 over 0, which is undefined. So the function doesn't exist at the value x equals 3. What that actually gives us graphically is something called an asymptote. And we call it a vertical asymptote because it's up and down. So when we graph them, we generally use a dotted line. And what winds up happening is these functions get what we call arbitrarily close to the value of x equals 3, but never actually touch it. So it gets closer and closer and closer and closer, but never actually touches that vertical line. Okay? So going back to my original problem, my domain, since that is what they were asking for in the first place, is going to be everything except for that value of 3. So we can say everything from negative infinity to 3, but not including 3. Okay? So there's our domain. Okay. All right, so what I want you to do, I'm going to give you a couple minutes. So you're going to pause here, and you're going to determine the domain for each of these functions. And you can do it graphically, or you can do it by simply looking at the equation or the function itself and determining what values of x would make my function undefined. So go ahead and pause here for a few moments. Okay, so the first function, f of x equals 1 over x. We can very quickly just graph that if we like. And here's my function. So it looks like I have a vertical asymptote that, oops, I didn't mean to do that, that runs along this y-axis. Okay. So the domain for this one is going to be from negative infinity to 0, but not including 0. That's the value of x that we're excluding because that's the value that makes the function undefined. Okay. So the next one, x squared, 1 over x squared. And I'm just going to change it right from here. There's my function. And again, it looks like the same thing is happening. It looks like it's getting closer and closer on either side of that y-axis, but never actually touching it. Okay? So again, same thing here. Negative infinity to 0, but not including 0. Okay? And then this one's a little bit harder. X minus 3 over x squared plus x minus 2. Here's my function. And it actually looks like I have 2 asymptotes here. It looks like I have one at 1. X equals 1. And x equals 2. I know one is more dashed than the other, sorry. Okay. So it looks like I have one at x equals 1 and x equals negative 2. So if I go back and I think about this algebraically, what I'm doing is looking for the values that are going to make the denominator 0. X plus 1, or x, sorry about that, x plus 2, x minus 1, which gives us the values of x equals negative 2 and 1. So my domain is going to be from negative infinity to negative 2, and then negative 2 to 1, and then 1 to infinity. Okay, so again, we're excluding the values of negative 2 and 1. Okay, so that's how we find domain of these rational functions. Okay. So, looks like I have a couple more here. So again, go ahead and pause and go over these ones, and we'll come back right back in just a moment. Okay, so looking at this first function, I see in the denominator I have 2x minus 6. So I'm wondering what value of x is going to make that function undefined, so I know what to exclude from my domain. So now I should be able to very quickly take that denominator, set it equal to 0, and solve. Okay, so I know that my function is not defined at 3. So again, domain is going to be from negative infinity to 3, but not including 3. Okay. Same thing for this next one. We already factored this, right? We know how this factors. X minus 2, x plus 1. So we know that x can't be 2 or negative 1. All right, so negative infinity to negative 1. And we always go smallest to largest. Union negative 1 to 2. Union 2 to infinity. There's my domain. Then this last one, if I look in the denominator, what's going to make this function undefined is a value of negative 1. Negative infinity to negative 1, union, negative 1 to infinity. Okay? So there's domain. So hopefully you guys got a hang of that. Okay, next page. All right, so let's talk about vertical asymptotes. So again, what happens I should have an extra p in it, sorry. What happens when my x value is closer and closer to 3 from the left and the right? We talked about that being a vertical asymptote where the function doesn't exist, right? So let's take a look at that graph again. Okay, is that the right one? -3, sorry. Okay, so as I approach 3 from the left, here's 3. As I approach it from the left, it's decreasing to negative infinity. As I approach it from the right, it's increasing to positive infinity. Okay, this shows a vertical asymptote. That's what that shows. Okay, when it shoots up and down in either directions to infinity. F of x decreases without bound as x approaches 3 from the left, and f of x increases without bound as x approaches 3 from the right. This shows that the value of x equals 3, there is a vertical asymptote. Exactly what I just said, right? So how do we determine a vertical asymptote? Basically, all we have to do to determine a vertical asymptote is to determine the value of x that makes my function undefined. So what makes my denominator equal to 0? So determine the vertical asymptote for the graph. So again, we're going to have a vertical asymptote where my function is undefined. So we have to look at the denominator. Okay, the denominator of this function. So here's what we're going to do. We're going to go ahead and factor both the numerator and the denominator if we can. Okay, so we know that the numerator doesn't factor, doesn't even have a GCF, so we're going to leave that, 2x minus 11. And the denominator, this does factor. This factors to be x plus 4x minus 2. Okay. So basically what we have done is we've figured out a way to very quickly look at our denominator and determine what functions are going to make this undefined. So if I look here, x plus 4, what function of x would make that undefined? And that would be -4. And right next to it, what function would make x minus 2 become 0 would be 2. So for this one, I actually have two vertical asymptotes. I have one at -4 and I have one at x equals 2. Okay. All right, so for this next one, it's a little bit different. Okay, so again, we're going to factor everything that we can. So if we start in the numerator, we're going to have, whoops, we're going to pull out a factor of x. And we're going to have x minus 4. And in the denominator, we're going to pull out a factor of x. And we're going to have x squared minus 1. And we know that that denominator can factor again. Difference of two perfect squares. Okay, so now we want to know what factors make my function undefined. So again, for that, we're just looking at the denominator. And we know that we have at x equals 0, it's going to make it undefined, right? Because 0 times anything is 0. At x equals -1, we're going to have a function that's undefined, right here, right? and at x equals positive 1. Now, some of you might have noticed that I share a value of x in the numerator and the denominator. I have a common factor. Okay? Because of this common factor, what this is able to allow us to find is something called a removable discontinuity. We also refer to it as a hole. Okay? So what winds up happening is, because of that, this asymptote gets rejected. Essentially what we have is we have a hole at x equals 0. Okay? To find the y value that goes along with this, I have to plug this back in. Okay? And we get -4 over -1, which is 4. Okay, so we have a hole at 0, 4. Okay, so that's what winds up happening when you have that factor. So you have two vertical asymptotes here and a hole at this point because of the common factors. Okay, moving on. Okay, I'm going to try one more, and then we're going to stop for the day. So to determine the vertical asymptotes, again, we're going to factor everything that we can. So you get x minus 2 in the numerator, and x squared, minus 5. So what values are going to make my function undefined? We know x equals 0 will make my function undefined from this x here. And then this piece, remember, to find where it's going to be equal to 0, we take and we set it equal to 0. Add over that 5. And we take the square root. And again, when we take the square root, it's always plus and minus. Okay. So we actually have 3 vertical asymptotes. We have one at x equals 0, at x equals the square root of 5, and x equals negative square root of 5. Okay, so we will pick up with this lesson next time, and we'll move on to horizontal asymptotes, but that's vertical asymptotes. So again, come prepared with any questions, and I'll see you guys tomorrow.